right, guys. So I have a question for you. You really had a choice here. You could have used sine, cosine, tangent, or you could have used special right triangles, and I don't believe that there is another way to do it, but if there was, you'll let me know. So raise your hand if you use sine, cosine, or tangent to solve these triangles. Raise your hand if you use the special right triangles. Okay, only 2 people have raised their hand. Does that mean nobody else did these problems? Or is there another way? What's that? You did sine, cosine, tangent? Yeah. Okay. Raise your hand if you also did sine, cosine, tangent. Good. Raise your hand if you did special right triangles. Okay, also good. We should get the same answers regardless. However, the whole unit circle is built off the special right triangle. So if you used the SOHCAHTOA, I want you to pay close attention to how to use the special right triangles so you can see. So we know that in the 45, 45, 90 triangle, what's true about these two sides? They're equal, yeah, they're the same. So these two are the same, and in geometry class, we called them both 1. We had 1, 1, and then if you solve with Pythagorean theorem, 1 squared plus 1 squared equals c squared, you get 2 equals c squared, and you get c equals root 2. So that's why the hypotenuse is root 2. So the ratio of the sides in the 45, 45, 90 triangle are 1 to 1 to root 2. In the unit circle, we use a slightly different ratio, but I am going to make those a little bit darker so you can see them. I'll show you why. Basically, in the unit circle, what we do is we want the hypotenuse to be 1, so we need to make the ratio just a little bit different. The 30, 60, 90 triangle, this one is not as obvious what the sides are, but if you think about the 30, 60, 90 triangle as half of an equilateral triangle. So here's an equilateral triangle. All right, and in the equilateral triangle, all the sides are equal. So if I said that this hypotenuse here is 2, that would mean that all the sides in that right triangle, in the equilateral triangle would be 2. So this would be 2, this would be 2, this whole side would be 2, and the blue part would be 1, because it's half of it. So now I can use 1 squared plus b squared equals 2 squared. B squared is equal to 3, and b is equal to root 3. And that's the reason why this side, the long leg, is root 3. I know that's really hard to read. So in the 45, 45, 90, it's 1 to 1 to root 2. And then in the 30, 60, 90, it's 1 to root 3 to 2. Those are your side lengths. Remember, the longest is always going to be the hypotenuse, and 2 is a bigger number than root 3. Okay, so using those, you can set up proportions to find your missing sides, and you should get the same numbers that you would get from SOHCAHTOA. So this is a hypotenuse, so I'm going to do hypotenuse over leg. So 14 over x is equal to root 2 over 1. And that would give you root 2x is equal to 14. Dividing it by root 2, you get 14 divided by root 2. So 3 sig figs would be pretty easy. You just put that in the calculator. Or you can actually get an exact answer by rationalizing your denominator. I get 14 root 2 over 2, which is 7 root 2. So this is 7 root 2. Now, if you got something from SOHCAHTOA that was a decimal, just type 7 root 2 into your calculator and see if you got the same thing. Can anybody confirm this answer, 7 root 2? You got the same thing?
7 root 2.
Okay, good. All right, how about y? If x is 7 root 2, what's y? Same thing, right? Because, yes, go ahead.
How do you, like, if we put in the number that we get from SOHCAHTOA, on a test or something?
How would you work backwards into that? Not really an easy way to work backwards into that. But the point of these triangles is to build up to the unit circles. So just try to understand it like from this right now. And I mean, you could always, guess and check your way there if that's what you're trying to do. But I think understanding it's a better course of action. But we can admit that we got the same answers from the SOHCAHTOA as we got from the special right triangle. And it just kind of makes us believe it a little bit more. All right, in this one, it's easiest to go from the hypotenuse to the short leg because the hypotenuse is twice as long as the short leg, 2 to 1. So the first thing I'm going to do is just say that my short leg is 10 because it's half of the hypotenuse. All right, so even though this was a big mess to solve, that one's pretty easy, right? And then if you know your short leg, you just have to multiply that by root 3 to find your long leg. So then your long leg would be 10 root 3. And again, you should have gotten in pretty close to 10 with SOHCAHTOA. Again, you might have a small rounding error. And then for the y, if you type 10 root 3 in, it should give you the same thing that you got for your answer. Does anybody have a question on those? Okay, so remember that for the 45, 45, 90 triangle, it doesn't matter how big that triangle is. If the angles are 45, 45, and 90, they're always going to have that proportion of their sides. The two legs are equal. The hypotenuse is equal to the leg times root 2. And the same thing with the 30, 60, 90 triangle. No matter how big it is, those proportions will hold true. Does anybody have a question I can answer about the warm-up?
Where are you getting these proportions from?
So I tried to build them with you, but I'm going to go over the way I built them one more time. One thing that we know about an isosceles triangle when these two angles are the same is that the sides opposite of them are equal, right? Just know that about isosceles triangles. So then I used Pythagorean theorem to find the hypotenuse. So I said if they're the same and we call them 1, you could call them 5 if you want, it doesn't matter. But let's say for simplicity we call them 1. It's 1 squared plus 1 squared equals c squared, and then I solve for c and my hypotenuse is root 2. One sec. Is it about that?
Couldn't you use the theorem to find the answer?
If you had two sides, you could. Oh yeah.
Well,
So
it's equal, so we would just divide it.
yeah, actually, you're right. So in this problem, you could have used Pythagorean theorem. Yeah. Good point. I like that. All right. For this one, in the 30, 60, 90, it's not as obvious what the ratio of the sides are, but when you realize that 30, 60, 90 is half of an equilateral triangle, then you can realize that whatever the hypotenuse is, this leg is going to be half of it because it's half of that triangle. I built the whole triangle around it. And so this is going to be one side of the triangle, and this is half of one side of that equilateral triangle. And then I used Pythagorean theorem here to find the length of this longer leg. And I got the root 3. All right, so we're going to move on to unit circle. In our last class, we talked a little bit about the angles and the radians on the unit circle. And today we're going to talk about the coordinates of the point. So if you imagine the unit circle that we talked about last class, and we put it on the coordinate plane where the center of the circle is 0, 0, every point on that circle is going to have coordinates. And we know some of the key coordinates, and we can find them using these triangles. When we draw a circle in the coordinate plane, and you consider an angle, here's an angle, that is formed by connecting the origin to a point on the circle. Okay, so here's an angle. You can talk about the sine, cosine, and tangent in terms of x and y. So this point has an x-coordinate x, which means that this side is x. And it has a y-coordinate y, which means this side is y. So if this is x comma y, it means I went x to the right and I went y up, whatever number those are. So the sine of an angle on the unit circle is going to be the opposite, which is y, over the hypotenuse, which is defined to be 1. The unit circle is called the unit circle because it has a radius of 1 unit. So it would be y over 1, which is just y. So if I know the coordinates here, then I know that the sine of this angle is equal to the y value. And something very similar is true for the cosine. The cosine is the adjacent over the hypotenuse, so it's x over 1, which is just x. And then the tangent is opposite over adjacent, so that's y over x. So here's my angle here, theta. The angle is formed by the line that connects to the point and the positive x-axis. So this is the angle I'm talking about, theta. All right, so when you know a coordinate on the circle, what you actually know is the x is the cosine of the angle, and the y is the sine of the angle. Cosine theta, comma, sine theta. Oh, and I guess that goes here. The coordinates of P can be written as cosine theta, comma, sine theta. All right, we have these reciprocal trig functions, and they will be used in later math courses, but like for right triangle trig, they just weren't useful because they're just the reciprocals of the ones you already know. So if you were given the opposite and you're trying to find the hypotenuse, you might use sine, or you could use cosecant, but it doesn't really make any sense to use cosecant when you already have sine. These are just reciprocals. So cosecant's the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent. Raise your hand if you've ever seen those trig functions before. Like seen them somewhere, maybe in a class. Okay, that's okay. It's good to know that they exist. We are going to talk about them a little bit. And you'll use them more in later classes. All right. So since cosecant is the reciprocal of sine, and since sine is y, cosecant is 1 over the y. Reciprocal, right? Since secant is the reciprocal of cosine, and cosine is x, well, secant is going to be 1 over x. And then what would be cotangent? X over y, good. All right. So here is our unit circle. Before we go ahead and find these coordinates, the coordinates are what's going to be new. I'm going to challenge you to try to remember a little bit of the degrees and the radians without referring back to your old notes. You do have old notes, but let's try to see what we can do without them, because eventually you're going to want to have this memorized. And it's not really hard to memorize because it makes sense. You do have to know that you start at the positive x-axis, right? Which is 0 degrees or 0 degrees or 0 radians. Let's see. And in terms of radians, it could be 0 degrees, 0 radians. And then if you go all the way around the circle again, you're at 360 degrees or 2 pi radians. So it starts here. Up here, we have 90 degrees, which is pi radians. No, pi over 2, my bad. Over here is pi radians, right? That makes more sense. A half circle will be pi radians and 180 degrees. All right, so I'm hoping that a little bit of it's coming back to you, and I can't write too much slower than you, but I do want to give you a chance to get ahead of me. So I'm going to pause for a minute, come see if anybody has a question, and then I'll come back and try to catch up to you. You're just working on the degrees and the radians right now. Okay. So we said this one right here is half of 90, so it was 45 degrees. And then we know all of these that are in the center are 45 away from either axis, really. So this is 45 more than 90, so it was 135. And then this one here is 45 more than 180, so it's 225. And then here, 45, oh, I didn't even fill this one in. This one is 90, 180, 270. And then this is 45 more than 270, so 315. So all of those angles that are in the center of a quadrant, they all have to do with 45. Any questions on those so far? All right, for this one, we said, okay, if you ignore this one, you can see that the 90 degrees is split into thirds. This is a third, this is a third, this is a third of the 90 degrees. So when you split them into thirds, then this is 30 degrees and 60 degrees. So it's 30, 60, 90. Then you add another 30 here, and you get 120, and add 30 to 120, and you get 150. 180, 210, 240, 270, 300, and 330. All right, we good so far? So now we have to do radians. So radians, you remember that we learned how to change degrees to radians. So if you had all the time in the world, you could literally just change every degree to radians. You could do, okay, 30 degrees is to how many radians? If 180 degrees is pi radians, and cross multiply, and simplify your answer. And you could do that for every single one. But really it makes much more sense than that. You don't have to solve for radians each time. I know that this is pi over 2, and this is half of pi over 2, so that would make it pi over 4. All right, it does take a little bit of fraction work. Everything that is going to be one of these 45 degree angles is also going to be an over 4. So this is 1 pi over 4, 2 pi over 4 simplifies to pi over 2. This is 3 pi over 4. 4 pi over 4 is just pi. This one's going to be 5 pi over 4. This is 6 pi over 4, but it simplifies to what? 3 pi over 2. And then 7 pi over 4. Okay, I'm going to wait because I can see people working on their pi over 4s. All right, this one is a third of half pi. So 1/3 times pi over 2 is pi over 6. So this is pi over 6. Then I go to the next one, and that's 2 pi over 6, but 2 pi over 6 is going to be pi over what? Pi over 3. And then 3 pi over 6 is pi over 2. This is 4 pi over 6, which simplifies to 2 pi over 3. 5 pi over 6. 6 pi over 6 is just pi. 7 pi over 6. 5 pi over 6, because this is 4 pi over 6 that's simplified. That's 5 pi over 6, and that's 6 pi over 6. 7 pi over 6. 8 pi over 6 is going to be 4 pi over 3. This is 9 pi over 6, and it's simplified already. 10 pi over 6 is 5 pi over 3, and then 11 pi over 6. All right, all the ones that are on the quadrants are pretty easy, because remember the radius of the circle is 1. So this would be 1, 0. That wasn't very easy to see though. 1, 0. This is 0, 1. Negative 1, 0. And 0, negative 1. All right, so now we get to the ones where we have to use our special triangles. So I'm going to draw a triangle to show you how this first one comes about. I'm going to take this point here. This is the point whose coordinates we're actually finding. I'm going to connect it straight down to the x-axis and draw that right angle in there. The 30 degrees refers to this angle right in here. This is the 30-degree angle, and that really makes sense. If you look at it, it looks like a 30-degree angle. This is a 90-degree angle. That means up here, this is a 60-degree angle. Now, if we use the numbers that we used on the first page, on the warm-up, we would be calling these 1, 2, and root 3, but I can't use those numbers because the unit circle has a radius of 1. So I can't do 1, 2, and root 3. Instead of 2, this needs to be 1, which is half of 2. So what you're going to do is take half of all of the sides. So this one was supposed to be 1. It's now going to be 1/2. And this one was supposed to be root 3. It's now going to be root 3 over 2. So we have a 30, 60, 90 triangle. I knew that this radius has to be 1, and so I used a proportion where I cut everything in half. Instead of 2, this is 1. Instead of 1, this is 1/2. Instead of root 3, this is root 3 over 2. Now I can use these numbers to write the coordinates here, because this is root 3 over 2 for the x and 1/2 for the y. With unit circle trig, we never put that in a calculator and get a decimal number out of it because that decimal number is rounded, and these are exact answers. So we always use root 3 over 2 and 1/2. And this is why most math teachers you can walk up to and say, hey, what's the sine of 30 degrees? And they'll say, oh, it's 1/2, because remember the sine is the y value. Okay? So just like you memorized your trig tables, your math teachers memorize their unit circle. All right, for the 45, it's getting messy to draw it in here, so I think I'm just going to try to draw it on the side. I'm going to draw it over here on the side, the 45-degree triangle. 45. Okay, so we had the hypotenuse as root 2, but we need the hypotenuse to be 1. So in order to make the hypotenuse change from root 2 to 1, we have to divide it by root 2. So remember here we divided everything by 2. We have to divide all the sides by root 2 this time. So these become 1 over root 2. Zoom in on that a little bit. Okay, so your 45, 45, 90 triangle, it was 1, 1, root 2, but we need the hypotenuse to be 1. So we divide all the sides by root 2. Now we know we can't actually have a fraction with a radical in the denominator, so we rationalize that denominator by multiplying by root 2 over root 2. So times root 2 over root 2, and that gives us root 2 over 2. So the x-coordinate is root 2 over root 2. Sorry, root 2 over 2. And the y-coordinate is root 2 over 2. Questions about the 45-degree one? I am recording this, so if you choose to, you can go back and try to listen to it a second time. The 60 degree, luckily, is not that hard once you have the 30 degree, because remember the 60 degree triangle is just the 30 degree turned on its side. So this time the short leg is 1/2, and then the long leg is root 3 over 2. So notice 30 and 60, it's the same triangle, and so the sides just got switched. All right, so we've done the hard work. Now we're just going to do a little positives and negatives. Let me know if you have questions about the first quadrant, because I want to answer those questions before we start doing the positive and negatives. Gabby?
Where do you get the root 2 for the hypotenuse?
So the hypotenuse of the 45, 45, 90, it was root 2 from our special right triangle, where the ratio is 1, 1, root 2, right? But we wanted it to be 1, so I needed to divide all the sides by root 2 so that the radius would be 1. Because remember, in the unit circle, the radius of is going to always be 1. Yeah. All right, so now what we're going to do is we're going to reflect this point over here. It has the same y value, but the x value turned opposite. So my x is negative 1/2, and my y is root 3 over 2. Remember, these are just points on the coordinate plane. So if I know this one, I know this one has an opposite x value, but the same y value. You can do the same thing here. Reflected across the y-axis, you're here, has the same y value, and then the opposite x value. And then reflect this one over here. Same y value, opposite x value. All right, same idea. You're going to reflect this one over here, adjust your positives and negatives, reflect this one here, adjust your positives and negatives. I'm going to give you a minute to work ahead, and then we'll go over those, okay? All right, so check your work, please. In the third quadrant, both the x value and the y value should be negative, and make sure you have the right point written down. This one, at 150 degrees, it reflects down here to 210, so these should be the same numbers. And then the 225 should have the same numbers as the 135, but they're both negative. And then the 240 should have the same numbers as the 120, but they're both negative. So make sure you have everything in the right order. Then in the fourth quadrant, all your x's should be positive, but your y's should be negative. All right, so we're going to fill out the tables at the bottom. It asks which trig values will be positive in each quadrant. And you can put the reciprocals in there if you want, but like honestly, there's not much new with the reciprocals, because if the sine is going to be positive, then obviously the cosecant is going to be positive because they're reciprocals of each other. So I think we'll just focus on sine, cosine, and tangent for a moment. Okay, so remember that every coordinate on the circle is going to be the cosine value as the x, and the sine value as the y. So in quadrant 1, both the cosine and the sine are positive. And if I do y over x, is it also going to be positive? Yeah. So, oops, they're all positive in quadrant 1. In quadrant 2, is it the cosine or the sine that is positive? Quadrant 2. I heard one vote. Anybody else? Quadrant 2, is cosine or sine positive? It is sine. Thank you. All right. So the sine is going to be positive. And then what about the tangent? Tangent is y over x. If I do a positive divided by a negative, is that positive or negative? Negative. So just sine. Quadrant 3. Is the cosine positive in quadrant 3? Is the sine positive in quadrant 3? No. How about the tangent? If I do a negative divided by a negative, is that positive? Yeah. So just tangent. And then in quadrant 4, which one is positive? Just the cosine, because just the x is positive. And then this is just a review of the fact that cosine is the x value, sine is the y value, and tangent is y over x. And then these are the reciprocal functions. Cosecant is 1 over y, secant is 1 over x, and cotangent is x over y. You might want to keep this page open because you're going to be using it, okay? So you can keep that page open. So what we're going to do is we're going to find the sine, cosine, tangent, secant, cosecant of these different angles. And we'll do two together. We're going to do this one and this one together. And then you guys will go back and do some of these others. All right, sine of 5 pi over 6. So find 5 pi over 6 on your unit circle. Is sine the x or the y?
Y.
Sine is the y, and so that would be what fraction? 1/2. So that was an easy one. The answer is 1/2. Where's 5 pi over 6 on your circle? Here, right? And then sine is the y value of the point, which is 1/2. Okay? Sometimes the problems are that easy. Cosine is the x, sine is the y. We're going to have to do a tangent together too. Okay, so sometimes they're easy like that. Let's go and do, before we do this one, let's do tangent together. Tangent of 4 pi over 3. So find 4 pi over 3. Okay. Tangent, remember, is y over x. So we're going to make that ratio negative root 3 over 2 divided by negative 1/2. Is that right? All right, so tangent is the y over the x. So I made that ratio. The over 2's cancel out. The negatives cancel out. And so I just have root 3 over 1, which is just what? Just root 3. So the tangent of 4 pi over 3 is root 3. If you wanted to check that on your calculator would have to be in what mode right now? Radian mode. And notice, like, sometimes you're going to be asked for degrees and sometimes radians, and so it's important that you switch back and forth as you need to. All right, cosecant 9 pi over 4. What is the problem we run into here? We don't have 9 pi over 4. Why? It's too what? It's too big. All right, so what happens is once you do the circle one time, it starts over again. So one time around is 2 pi, right? So a full circle is 2 pi, and 2 pi is 8 pi over 4. Okay? So after I do 8 pi over 4, how much more do I have to do to get to 9 pi over 4? Yeah, 1 more 45, which is just pi over 4, right? All right. So we say that 9 pi over 4 is coterminal with pi over 4, and that's the angle we're going to use. Coterminal with pi over 4. Okay, so terminal is like end, right? Coterminal means it ends in the same place. Let me go to my circle for a minute. If I want to do 9 pi over 4, I start here, right? I go around a full circle, and then I stop right here. That's 9 pi over 4. So it ends in the same place. And it has the same coordinates as pi over 4. Have you ever seen like a gymnast who can do like a flip that's more than 360 degrees? Like they go around more than once, right? If you do like twice, it's 720 degrees. Okay? You can do more than 360 degrees. You are not limited to that. Yeah?
Yeah, I you know what, I agree there. I think we should just, stick to 360.
All right. Guys, here's the key though. If you have something bigger than 2 pi, you just keep going, and wherever you stop, that's what you use. So this is 2 pi plus another pi over 4. So we're using this, the root 2 over 2, root 2 over 2. Yep.
So then
All right.
there's another dividing the diversity.
So we have to do reciprocal of sine, right? So it's 1 over y. Cosecant is the reciprocal of sine, right? Okay, so cosecant is 1 over the y. The y of the point is root 2 over 2. So it's 1 over root 2 over 2. So the first step I would say would be to simplify 1 over root 2 over 2 to be 2 over root 2. 1 over is just means reciprocal. And so this becomes 2 over root 2. And then we can't have a radical in the denominator, so we rationalize by multiplying by root 2 over 2. Root 2 over root 2. You get 2 root 2 over 2. Which is just what? Just root 2, thank you. All right, so that was a complicated problem, I will admit. But let's go through the pieces of it. The first thing that was hard was that our angle was too big. So we figured out that 9 pi over 4 is coterminal with pi over 4. That was the point we're using. Then we recalled that cosecant is 1 over the y value. So we found the y value is root 2 over 2. And then the last thing that was hard was that we had to simplify 1 over root 2 over 2. So that took some steps, and we ended up with root 2 as our final answer.
But how did the 1 become a 2?
So I'm going to show you on the board how to divide this and simplify this. But if you're good with this, you guys can move on because I want everybody working on these as well. All right. Cosine of pi over 3, you found pi over 3 on your circle, and then you chose the x value, which was how much? 1/2? Did you guys get that? Okay. Yes. Uh-huh. All right, cotangent of 7 pi over 4, so I'm going to find 7 pi over 4. And cotangent is going to be x over y. And so I have root 2 over 2 over negative root 2 over 2. Is that what you guys got? Okay. Basically, you're dividing by the same thing except for the opposite. So instead of positive 1, your answer is what? Negative 1. You don't have to do a lot of fancy, like, keep, change, flip stuff. You can just understand that you're dividing by the opposite of a number, which is always going to give you negative 1. Secant of pi. So we're going to find pi on our unit circle, and then secant is 1 over x, right? The cosine? Okay. And then the x is negative 1. So you guys got 1 over negative 1, which is what? Am I wrong? No? Okay.
Oh, okay.
What if I had asked the cosecant of pi? It would have been 1 over 0. What would we have written for that? What's 1 over 0? Undefined. Very good. So if you ever get 1 over 0 as your answer, just write undefined. Okay? Can't write no answer. You can't write any other thing that you make up. The answer is undefined, that word. Okay? All right, moving on. Find the exact value of theta for all angles between 0 and 360 degrees. That means that there's probably more than one answer. Did anybody try the first one? Sine theta equals 1/2? Look at your circle. Where on your circle is the y value 1/2? Okay. Where is the y value 1/2? I heard 30 degrees, and that's right. And 150 degrees. Good. And notice they asked for angles between 0 and 360, which means they want us to write down the degrees, not the radians. Okay? So it was 30 degrees and 150 degrees. All right, let's do the tangent. All right, root 3 over 3 is positive, right? And the tangent's positive in which two quadrants?
X and Y. Or not.
If they're both positive, right, in quadrant 1, yeah, that's true. All right, and then Sophia reminds us also quadrant 3 has positive tangent because negative over negative is positive. So we're going to be looking for angles in quadrant 1 and in quadrant 3. We know it's not 4 pi over 3 because we already know that the tangent of 4 pi over 3 is root 3. So what angle should we try? What would be a good one to try? Look at your fourth quadrant. If it's not 4 pi over 3, what should we try? 7 pi over 6. So let's try 7 pi over 6. So looking at 7 pi over 6, and we're just trying it. Your coordinates are negative root 3 over 2 and negative 1/2. And tangent is y over x. So y over x is negative 1/2 over negative root 3 over 2. The negatives cancel, the 2's cancel, and I get 1 over root 3. Does 1 over root 3 simplify to root 3 over 3? Well, you have to rationalize it, right? Times root 3 times root 3. It does. Root 3 over 3. So 7 pi over 6, which is actually, I need the answer in degrees. How many degrees is that? 210 degrees. So 210 degrees works. Does anybody have an idea if 210 degrees works, what's the other one that's going to work in the first quadrant? It is 30 because if you look at the 30, it has the x and the y in the same place. It's just that they're both positive, right? 30 degrees and 210 degrees have the same coordinates, just that in 30 degrees they're positive, and in 210 degrees they're negative. So 210 degrees and 30 degrees are your answers. All right, try cosine negative 1/2 and secant negative root 2. All right, folks. So cosine is negative 1/2. Did you look for where the x is negative 1/2? Okay, so negative is over here. So it looks like 120 and 240. Is that what you got? Okay. 120 degrees and 240 degrees. Yeah. All right, secant is the reciprocal of cosine, right? Oh, thank you. Still frozen. Okay, secant is the reciprocal of cosine. And we're looking for where the cosine might have something to do with a root 2, and a negative, in fact, right? So in which quadrants is the cosine negative?
Left side?
Yeah, on the left side. Very good. So we're only looking on the left side. And which angles have a root 2 in their coordinates on the left side? 135 and 225. So we're thinking it might be both of these, right? Because we've had 2 angles so far. So let's just try one of them and make sure that our assumptions are making sense here. So the cosine would be the reciprocal of negative root 2 over 2. So 1 over negative root 2 over 2, which we've done this before, right? That becomes 2 over negative root 2. We've done all these steps before. And then we rationalize. And so we had 2 root 2 over negative 2, which is negative root 2. So we were right. So that was from 135 degrees. And we said it was also going to be 225 degrees. Okay. This next one is asking you to do pretty much the same thing, only to give your answers in radians. So let me give you a few minutes to work out those last four, and then we have something new on the next page. All right, so sine theta equals 0. That happened at 0 radians, pi radians, and also at 2 pi radians. All right, cotangent of theta is root 3 over 3. So we've kind of spent some time thinking about tangents and cotangents, right? The places where the tangent is going to be root 3, the cotangent is going to be root 3 over 3. Those two numbers are reciprocals of each other. So I know that if the tangent of 4 pi over 3, where's 4 pi over 3? I'm going to write tan theta is equal to root 3. Okay? If I know the tangent of this angle is root 3, then I know the cotangent, the reciprocal, is root 3 over 3. And so that's one of my answers, 4 pi over 3. The other answer is going to have to be in the first quadrant, right? Did anybody find the first quadrant answer?
Pi over 3.
It is pi over 3. So notice 4 pi over 3 and pi over 3. They have the same numbers, just one is positives and one is negatives. Looking at 4 pi over 3 and pi over 3. Same numbers, just these are positives and these are negatives. And so this is the other one that has a cotangent of root 3 over 3, pi over 3. All right, tangent is equal to 0. Remember, tangent is y over x. And so that basically means the y has to be 0, because 0 over any number is going to still be 0. So we're looking for the angles where the y is 0. So if you haven't found it yet, go back and find it. Find the angles where the y is 0. Same ones we found before, right?
Yep.
0, pi, and 2 pi. And that cosecant's a big mess, isn't it? Cosecant is the reciprocal of sine, and so that's going to be 1 over y. Notice the negative there. Sine's negative in which quadrants? Where's the y negative in quadrants 1, 2, 3, or 4? 3 and 4. So we're looking in quadrants 3 and 4. And we're looking for an angle where 1 over y might give us this. Let's find something that we want to try. Okay, so do you think that 1 over y, this might be a number whose reciprocal would give us, what was that again? Negative 2 root 3 over 3. It's worth trying, right? Because it has the root 3 in it. So we're going to try 5 pi over 3. And it was going to be 1 over the y, and the y is negative root 3 over 2. So the reciprocal is going to give you negative 2 over root 3. You're going to rationalize it. Negative 2 root 3 over 3. So did 5 pi over 3 work? So that's one of them. And now we have to try to find one in the fourth quadrant, in the third quadrant that's also going to work. It is, yeah. So since 5 pi over 3 worked, 4 pi over 3 is also going to work.